Hi everyone. Thanks for coming and for finding seats. Today we're very happy to have Kosuke Imai here. He is a professor in the politics department at Princeton University, and today he's going to be presenting using a probabilistic model to assist merging of large-scale administrative records.
Right. Yeah, thanks for coming and thanks for the introduction. So today I'll be talking about really boring topic of how to merge the data sets. So I'm excited to see a lot more people than I expected. This project is joined with Ted and Amaretto and Ben Fifield, who are both graduate students at Princeton, and they've been doing great work for this project. Okay, so just to motivate the whole talk, in any given project, right, so social scientists to be used in multiple data sets. So we rarely rely on just a single data set. We have a bunch of data sets and trying to merge those data sets to do the analysis. So if we can do this easily if there is a common unique identifier. So if there's the ID, then whether you use R or Stata or any other program, you can just merge, right? No problem, right? But what about if we have no unique identifier, right? So then we have to start using actual variables information about the records to do the merge. What if we had millions of records, right? The voter files, that's going to be my primary example, where we have 160 million voter records. How do we merge that? It's at this point, it can't really merge by hand, right? We need some algorithm that's scalable. And variables often have measurement error and missing values. They're not perfect, so names may be misspelled, certain information may be missing. So if we just use exact matching, then what we end up with very few matches, right? And that would be problematic. So we want algorithm that can accommodate measurement error missing data. We also know because of these issues, merging is an uncertain process, right? We may falsely match to records, or we may not actually find the true matches that exist in the data. So we want to sort of quantify uncertainty and error rates. Right? So all of this, I think, motivates that we should be using the probabilistic model as a way to do this. And the reason why I got into this project actually isn't really motivated this way, and the actual motivation and large part of this talk is going to be talk about how to apply this to national voter files. So I had this opportunity to gain access to the entire national voter file, and there's 2 time periods, or actually multiple time periods, these voter files are collected. So the question is, how do you merge multiple voter files? And I've made some progress, and it's not entirely there yet, but I want to report some of the progress I made and get some feedback from you guys. Okay, so data merging, sounds like a really boring topic, but can be really consequential, actually. So in my field of political science, there's the American National Election Survey that's conducted every once in a while after the election. And if you just look at the self-reported turnout, it's almost 80%. But we know from the administrative records that the actual turnout is only about 60%. So there's a huge gap between the self-reported turnout from the surveys and the actual turnout. And some people think that the electronic validation of the survey response by merging the survey with the voter files would be the way to go. Right? You don't want to rely on self-reports because people may lie. They may say they voted even if they didn't. Some other people says in this matching process, there's lots of errors. And the validated turnout look like actually more accurate, even though they may not be. So the challenge of this type of process is that you have to find 2,500 survey respondents in 160 million registered voters. That's less than 0.001% of the registration records. So it's really they're finding needles in the haystack type of the problem, right? So it's a difficult issue. And furthermore, the problem is that the fact that you were able to match is not the same as you actually voted, right? The fact that you couldn't match is not the same as you didn't vote, right? It may be the algorithm failed, to find someone in the voter registration record, maybe that person actually voted, right? So we can't really conflate the failure to match with whether the person voted or not. So again, thinking about the errors, how much errors are involved in this process is going to be very important. Okay. So it turns out when I started this project, I looked around what the other social scientists do, and it turns out that many social scientists use deterministic methods. So the couple papers that I cited in political science somehow define the similar observations and then decide if they are similar enough, they're called matches. There's a lot of proprietary methods. The Catalyst, I think, is the vendor that's making a lot of impact in this area. The ANES relies on like Catalyst match, for example. But the problem of proprietary methods is it's unclear what it is. It sounds like deterministic methods, but there's all sorts of things going on that we don't know. So the problem is these methods, as I described, not robust to the measurement error and missing data. There's no principal way of deciding how similar is similar enough, whether you call it match. And then in the case of proprietary methods, there is a lack of transparency. So as a researcher, if these process is really consequential, it's problematic that we can't say even how we did it. Well, what I want to advocate is that there is actually going back to 60s, there's a large literature in statistics we can exploit to do this type of record linkage probabilistically. So the original model actually was proposed back in 1969, and since then there have been some advancements, but it seems all the methods are really based on this nice idea that Ferrari and Santer had back in 69. And what's nice about this is that enable the control of error rates. So what I'm going to do in this talk is I'll show you how we apply this algorithm to some of the data sets that we had of large scale. However, when we first tried to use this method, the problem was that the current implementation that were out there did not scale to large data sets. So we had these 160 million voter records, and there's just no way that you can use the current implementation to do the merge. We also found that in practice, missing data are often treated as disagreements. So if you have a say middle name missing, then in another record you find some other observations that has missing data, it was coded as missing. The middle name is different, even though one is missing and the other one is measured. Okay, and there's, I think, this is sort of still ongoing research, but there's a lot of information that we can actually incorporate to improve these estimates. And that's somewhat a conjecture, but for example, we know, the rough moving rates, like how often people move from one state to another from various sources. So we might be able to incorporate that type of information when we are doing matching over time, for example, because people move from one place to another. Okay, so just to review this canonical model, Ferrari-Santer model, it's a very neat model. So there's two data sets, D1, D2. Each has N1 and N2 observation respectively. There's a K linkage variables in common. So these are the variables that you're going to use to do a match. So in my example, it would be like a name, address, and birthday, and so on. As we're going to consider all pairs, right? So it's a pairwise comparison. And obviously, at some point, you cannot do all pairwise comparison. Once you have, say, 5 million observations, there's no way that you can do all comparisons. So you end up doing some type of blocking to restrict the comparisons. But for now, I'm going to present the model using this pairwise notation. And basically, once you pair these observations, we are going to look at each linkage field and then see whether the two observations have the same value, whether you have the same name or a different name. And depending on the field, so for example, the name, there may be some spelling errors, so you might want to also quantify some similar names. And there's different ways to quantify this. There's the distance measures that you can come up with. So you can call from 0 is completely different to LK minus 1, which is identical. So if it's 3 category, 0, 1, 2, 0 being different, 2 being identical, and 1 is somewhere between. Okay, so you can categorize the similarities in whatever the granularity that you like to do. So you're going to do this for each field, each variable that you're going to use to do match. Okay, and the key of this model is that there's a latent variable. So the binary latent variable that you don't know, you don't observe. So if the pair is actually matched, it's 1. If it's not matched, it's 0. Okay? And when you have a missing data, you might have a missingness indicator. So that's basically the setup. So once you create the pairs, you look at each variable within the pair to see if they are the same values or different values or similar values. And we're going to try to figure out whether that pair is actual match or not. So this one is not observed. That's something that you're going to infer from the data. Okay, so typical model of this type assumes independence for computational efficiency. So if you don't make this assumption, it really doesn't scale to millions of records. You have to account for the correlation across fields. And so most of the implementation would make independence assumptions, independence across pairs, independence across variables. Okay, so these are the assumptions that in principle can be relaxed, but for the computational efficiency that's being imposed, furthermore, we're going to assume that it's missing at random. So conditional on, actually it's at the latent level. So conditional on the variables that you use for matching and the matching indicator. So whether it's matched or not, the distribution of the missingness and the actual values of the agreement patterns are independent. Okay, so with these three assumptions, essentially you can ignore the missing values. Instead of coding as a disagreement, you can essentially ignore the missing values when you're doing the calculation. Okay, so the model is just a very simple non-parametric mixture model where there is two categories. Either it's a match, and given the match, what's the probability of agreement for each field? Given the unmatch, what's the probability of agreement for each field? And it's just a simple mixture model. Okay. And you can basically do the EM algorithm to do this calculation. All right. So I'm going to describe quickly how we implement this in a case where you have millions of records, so that is scalable. And we have this R package that's it's sort of still beta version, but if you're interested in, you can email me too. And then you can try it out. Eventually, we'll soon release this more publicly. Okay, so the way that this EM algorithm works is the sufficient statistics. So all the statistics that you need to calculate is actually just the number of pairs with each observed agreement pattern. So you have to count how many pairs have all identical values across all fields. How many pairs have names are different, but everything else is the same? How many pairs have all different? Like, you just basically have to count. So the question is really like how quickly can you count? Right? That's basically the game. Right. So there's a computer science. It's a computer science 101 technique called hashing, which basically matches the patterns of the agreement with the unique value in order to count. And so what we do is that for each, so K stands for each field, so each variable that we use to match. And we basically going to, it's a little bit involved expression, but basically what it does is that for each pair, so these elements are pairs, so N1, there's N1 rows, N2 columns, so it's all pairs. And if the values are different, if they disagree, that is gamma is equal to 0, then this value is going to be 0 for any given field. If it's actually agree, then it has a unique value where it's raised to the power of 2. Okay, so this ensures that every patterns when you add them up, ensures that every observed agreement pattern will have a unique value. Yeah. So this is like a hashing technique, like counting technique. When I was in elementary school, like I learned how to count this way. But it turns out it's like a computer science technique that's like you learn in a computer science class. So I thank my elementary school teacher for showing me how to count. So this is basically hash value and keys. And what's nice about this in our setting is that this matrix is very sparse. So if you think about all pairwise comparison, most of them are not much, unless there's a lot of duplicates, right? So most of them are 0. And also that the number of observed agreement pattern is very, very small. So it's not that every agreement pattern is often realized. It's only certain agreement patterns are realized. So once you recognize this fact, you realize that this matrix is very sparse, so you can use the sparse matrix operation. And then adding them up doesn't really increase the number of unique patterns. So this H matrix is also very sparse. So with sparse matrix, the lookup time, that is like the time to count, is basically the number of unique patterns observed, which is much smaller than the all possible patterns that you could have observed. Like in a typical data set, the number of unique patterns you actually observe is much, much smaller. Even though if you have, say, 0-1 coding, disagreement 0, agreement 1, if you have 5 variables, it's 2 to the 5 possible patterns. Not all patterns are often, they're not observed. Only a certain patterns. There's a lot of zeros, and there's a lot of identical all ones, and then there's some small number of patterns that are less than that. Okay, so anyway, and if you have many linkage fields, so in our application, the number of linkage fields is like 5 or 6. So we can do this exactly. If you have hundreds of variables that you're going to use to match, so in some cases you might have that. In those cases, there's a technique called mean hashing and local sensitive hashing, which is an approximate technique to do this type of hashing. So if you have that type of situation, you can do this. And what is all nice is that once we do this counting, the EM algorithm is like super simple. And so that part doesn't take a time at all. But it's just the counting part. It's like 99% of computational time is literally counting this table of agreement patterns. Okay, so just to quickly, yeah.
So just to be clear, so for several of your pairs, if I'm understanding this table right, for most of your pairs, when you look at one of the fields, they're just clearly different. And when it's clearly different, you score it as a 0. So
right.
Basically, all of the zeros in these matrices mean that there's no doubt that these are different entities.
If it's clearly 0, yeah, that's right. But sometimes it's unclear whether names are different or similar enough. It could be misspelling. So
But if it's a misspelling, then you would end up with one of the other levels of your.
Right, that's right. So you ended up with depending on this is a level. So depending on the number of levels you have, you end up with a 2 to the whatever that number.
Okay, so the hope is when you look at similarity of a field that if they could actually have been a misspelling or something, that it will not get a score of 0, it'll get a score of
Right. So that's your decision. So there's a standard measures that people use, oftentimes like Jarrow-Winkler distance that basically compares the two names and then how many transpositions you have to get from the one to another. There's other distance measures. So you might, and then people do there's a cutoff that people use to decide how similar is similar enough. So in this standard setting, you have to discretize it. You could imagine modeling the continuous measures as well. But when you have this many observations, it's just Matt.
Are you assuming here anything about how many true matches there are for the given records? Like, is it so? There could be duplicate entries on it.
And you can estimate that. So that's the sort of nice part of this type of model is that you can estimate the true number of matches as well. And I'll show you the applications of this in a minute. Okay, any questions? Yeah, so this sort of counting exercise that we've done. And so just to give you a sense of how fast, again, this is all about by hashing. So there's like the first package we tried in R, it's a record linkage package, and you can see that this is a data set size matching two data sets of 30,000 observations, and you can see it's an exponential increase, but ours is more or less linear. And so this is no blocking, single core, so 30K observation, two data sets, margin, about like, I don't know, 15 minutes or so. And the parallelization is possible. That's another nice thing about this type of method is that you can parallelize. The counting process can be parallelized, and the EM algorithm also, or EM actually doesn't take much time at all, so that doesn't matter. Okay, all right, so that's basically the runtime. And what's nice about this probabilistic model is that you can control the error rates. Okay, so two error rates we're looking at is a false negative rate. So false negative rate is the number of true matches not found, right? Divided by the number of true matches. So how many matches did you miss? Okay. You can also calculate the false discovery rate. So among the pairs that you call matches, how many is actually false? So these can be estimated from the data. And with this many data, there's almost no uncertainty. So they're very precisely estimated. We typically control FDR, so we make sure that FDR is small, and then we are interested in how big the false negative rate is. Okay, so first thing that we do is the simulation studies, and I don't want to spend too much time on this because I want to go to the applications. But what we did is basically we took the photo files from California, looking just at the females, so 8 million records. We basically only took the records with no missing data and created two duplicate data that are actually has actual matches. Okay. We used first name, middle name, last name, date of birth, address. You want to split house number and the street name separately, and zip code. Okay. So we had several scenarios. We had two equal size of data sets. We had an unequal size of data sets. And we also tried different missing data mechanisms, missing complete at random. And I can give you all the details, different level of missingness. But we also added the noise to like change the name a little bit to see how robust it is. And what I'm going to show you is that what we find is that as long as the missingness is not really severe, that these methods actually seems to work extremely well. So here is just one example of that. So on the top, you see the false negative rate. And on the bottom, we're looking at the turnout. So we're looking at the turnout rates and then see what's the turnout rate of the observations that are actually found in two simulated data sets. And there's different threshold based on false discovery rate. So you can decide where to call the match or not match based on the false discovery rate. So for each agreement pattern, you get the false discovery rate. So you can sort them by the false discovery rate and then decide how far down you go. And the red is the exact match. So if you insist on exact match when you have lots of missing data, you basically have a lot of false negative rate because you miss a lot. You insist on the exact match. But you can see that the EM algorithm does really well across different patterns of missing data. You can also just use, instead of calling whether match or not, you can also use the posterior matching probability and then calculate the weighted average. So when you do the turnout, you can do the weighted average of turnout. So this keeps all the data. So instead of calling the binary match or non-match, you can just calculate the weights, use the weights to do the weighted average. So the one observation can be matched with 3 different observations with different probability, for example. And then you can just use the weighted average to compute the turnout. And so that's green. And you can see that green maybe is best performing. Even data is not missing at random, the bias is much smaller. So when the data is not missing at random, when you start calling match or non-match strictly, then you start missing certain type of people who are either voting more or not voting, whereas the weights allow you to capture those observations. Okay. Another thing I think it's interesting is that you might think these estimates of false discovery and false negative rates aren't that accurate, but what we found in our simulation is that they're pretty accurate. So here, because it's a simulation, we know the true false discovery rate, and then we plotted that against the estimated false discovery rate. And so if you're in the 45-degree line, you're basically getting the right answer. And the blue is the case when the missing is treated as missing, whereas the black triangle is the case where missing is treated as disagreement. And you can see the blues are almost all the time in the 45-degree line, whereas the blacks tends to be off in some cases. And moreover, the error rates are smaller if the missing is not missing is treated as missing as opposed to treated as disagreement. Okay, so we've done a bunch of simulations. We think that this method can actually accurately recover some of these error rates. So now I want to go to the applications and show you how it works in practice. Okay, so the first thing we did was to merge survey with administrative record. Okay, so there's a paper by Hill and Fuber who studied difference between donors and non-donors among CCS, which is the one survey that's actually run out of Harvard. So what we did was that we matched CCS respondents with DIME is a data set of donors, political campaign, the contributors. So it's a public information, and there's a Stanford political scientist who clean it and then turn it into a data set. Okay. The CCS uses a proprietary method and basically treats non-matches as non-donors. But again, this might be problematic if you actually misses some matches, right? So those people may have donated money, but they weren't matched, and hence treated as non-donors. Donation amount, they coercion so that so there's a self-reported donation amount that's reported in the CCS. They coercion it so that you cannot identify individuals by merging with the public records. But this, privacy issues is a big actual issue in the actual practice. All right, so what we did is we were able to match, this is the CCS. CCS were able to match 8% of out of 55,000 respondents. So this is a big survey, so you had 55,000 respondents. Okay, and there are some discrepancies between self-reports and donations when the CCS did the proprietary methods. So only 25% of self-reported donors are matched to the donation record. Democrats seems to be better matched than Republicans. So we basically asked YouGov, the company that runs the CCS, to apply our algorithm to see what happens. Okay, so margin process involved 5 million unique contributors with 51,000 respondents. If you do exact match, you only get 0.33% match rate. So exact match is a bad idea. We blocked by state and gender, and then we did some blocking using the k-means to further reduce the size of comparison, about 500, 3 to 500,000 observations. And we used the first name, middle name, last name, address, and zip code as a linkage field. Our method is pretty fast, so it took 2.5 hours using a dual-core laptop. So that's not too bad. So what you get is that once you run the algorithm, I'll just give you a sense of what you get. As an output, what you get is this type of table, where 2 represents the exact identical value, and 1 is similar. In this case, we have 3 levels, and 0 is completely different. So you can see for first name, middle name, last name, these pairs are matched identically across all fields, and then the posterior probability of matching is 100%. Okay, so this is the way that's literature. In the literature, it's used. It's a likelihood ratio, but I find the posterior is easier to interpret. And this one is NA is missing. The middle name is missing, and the first name is similar, and the street name is similar. House number is the same. Zip code is the same. Last name is the same, and that gives a 93% probability of matching. Okay, and the last one is the first name and last name are the same, but the street name is different. House name is different. Zip code is non-existent. Middle name is non-existent. That gives you 1% probability of match. Yeah.
Is there some? I mean, maybe I missed this, but is there some way of kind of encoding and ordering in terms of how much error there's likely to be in the different variables? So it's like, we might think that middle name is like a bad.
Yeah.
There's a lot of measurement error there.
Right. So that gets automatically adjusted in the data.
Okay.
But what we might not capture is that some names are more common than others. So if you have like first name John, you might be more likely to be 4-3 matched. Later I show you can easily incorporate that as a prior. So you can downweight some of the common name match in the prior, and it's so you can. We are basically we actually use the census name list to downweight some of the common name matches. Yeah.
So you mentioned you could like incorporate outside information like integration rate.
Yeah.
Talk a little bit more about how that.
Yeah, I'll talk about that very at the end. We are sort of still exploring, but okay. So that's basically the table you get, and you decide how far you want to go. Okay.
If there's,
Yeah.
So if you're matching your first data set to your second, and your second had 2 people that had the exact same first, middle, last, street, house, zip, would they each get a posterior of 1, or would you get a posterior of 0.5 for each of them? Like if there was sort of if there was 2 things you could match to.
Right. So you could, yeah. So because the pairs are assumed to be independent, so you get a different posterior for each pair.
So the model does not take into account that once you're matched to someone, that
Yeah.
that's right. Then the
Which
other
may
one's
be good or bad. So sometimes there's a lot of duplicates in the record. So you want allow the multiple matches. If you restrict to be a single match, then all the independence assumption won't hold.
Right.
So that will complicate the computation quite a bit. So what you can do is you either pick the largest posterior, or what we are doing in practice is sample one of the pairs according to the posterior probability, just so that we have still nice data set with single match.
So for any particular entity, you have the specter of probabilities, and you sort of
Right.
draw.
Right. Or you can weight by the posterior probability for whatever the quantity of interest, but that gets complicated when you have a lot of the observations. Okay, so that's basically the process. So this is the results of the CCM match. So we compare with the proprietary method. So the match rate is how many of the CCS respondents are found in donation record. So we found about 99% if you use the liberal threshold. I think this is like 85% posterior, 85% or above. This is 90%, 95%. And you can see that you can calculate the false discovery rate and false negative rate for each one. So you see that we are missing a lot, right? So potentially there's like 30% of donors are maybe not found in donation record. Although we are not making too much of the false discovery rate, right? False discovery rate is about 1% or less.
Can you talk again about how you calculate the discovery and the negative
Yes.
rates?
Yeah, so this comes all from the model. So the model has the probability of agreement giving you are either matched or not. You also have probability of match. So with the Bayes rule, you can calculate the both of these quantities. So it's coming from the model parameters. You can also estimate the proportion of the true matches from the model, and it's estimated to be 12%. So we are matching 9%, or a little bit maybe less, depending on the threshold. And the model is estimating the true proportion is about 12%. And that comes because we are thresholding at, say, 95%. So we're ignoring some people who are potentially matched. Okay. All right. So that's basically what you get. So it sort of allows you to get a sense of how many people you're missing, and how many people you're wrongly capturing. So here's the posterior probabilities. You can see like there's quite a separation. So good data set, if you're trying to merge, you have a large number of probability close to 1, and then you have large number of probability close to 0. I didn't show it because this is only the ones that are matched. And there's a flat region in the middle. So there's a nice separation that happens in this case. So this is the cases where both proprietary method and our method code matches. So in those cases, we have 3,000 cases like that, and it's almost 1, the posterior probability. There are some observations we code match, but the proprietary method code no match. We see that still. We still see that 900 observations have very high posterior probability of matching. And if you actually look at the agreement patterns, you probably feel pretty comfortable calling them as match. This is the cases where proprietary method for some reason called no match, called match, and we call no match. So according to our posterior probability, it's very unlikely to be a match, but the proprietary method for some reason called that as a match. That could be that our estimates aren't quite accurate, or they may have other information that they're using to match. So I'm not saying that proprietary method is necessarily bad, but there's these differences.
So among
Yeah.
the 3,000 cases, 800 are matched by proprietary method.
So we matched about 4,500, and out of that, 3,700 are also called matched by the proprietary method, and 900 are the ones that we call match, but they didn't call match.
Spot checked those
Yeah.
the ones that they matched, and were you able to see why they matched and were they true matches? Maybe that will help it.
So from just
It has
looking
the
at
other-
from looking at the fields, like you would think, why would you call this a match? Like the names are different than street name, but they may have had some other information, because these private companies know a lot about you, like your credit rating and other things. So we only use these fields that we use for match, and if you're just looking at those, it doesn't strike me, but maybe you married and last name has changed and we don't have that information. So, we don't insist on exact match, but we don't use that information in this
But
matching
you don't know for
process.
sure if they used outside sources or not.
Right. So I want to be careful that I don't call this like failure of proprietary method. It's hard to know. But certainly I feel again this I feel these observations I feel comfortable they're matched, but you never know. Okay, so here is the correlation between self-reported donation and the actual donation amount from the public record, okay, among the people who matched. So on the, again, these are liberal threshold, strict threshold, and this is the common matches. So among the observations that it's on the log scale, among the observations that we call match, there is pretty high correlation between the self-reported donation amount in the survey and the donation amount that's recorded in the administrative record. So a correlation of 0.75. If we look at just the ones that we called matches and the proprietary method didn't, its correlation is about 50%. If we only look at the matches where proprietary method called matches, but we didn't, you see that it's 40%. Okay, so that's sort of the interesting sort of contrast. But at least the people don't seem to be lying too much as when it comes to that.
Reporting
People are
less.
underreporting.
Yeah, that's what's surprising.
People are underreporting. Yeah, that's right. Yeah. But maybe that the people who are more likely to underreport are likely to be matched. But yeah. I mean, I think more sort of little scary part is that about 12% is estimated to be the donors, right? So CCS has a much larger proportion of people who are donating than the American electorate. Right? A lot more, right? So that they're much more politically active, which I guess is not surprising. Like, why would you do that survey if you're not politically active? So there's one question you might think is like, okay, so once we do this match, how do we run regression, right? So that's like social scientist wants to run regression. So post-merge analysis. So suppose we're interested in regression model of interest, and M star is the real match that we don't observe. So we can make few assumptions. The first assumption is no omitted variable for merge. So given the variables that we use to merge, this independent variable is independent of the true match. We can also assume, basically this is saying the merge is good. You're doing a good job doing merge. And there's no omitted variable for the outcome. So once we condition on these two things, the variables that you used for merge and the outcome are uncorrelated. So there's no omitted variable. So once we make this assumption, all you have to do is the weighted linear regression, where it's actually not really weighted linear regression, but you can replace the M star, the true match that you don't know, with the probability of match. Okay, and under this assumption, this will give you the right answer for the beta. And if it's a maximum likelihood, you can do the weighted maximum likelihood, where the actual match is weighted by the probability of posterior probability of match. And
I'm sorry. What is M star?
So M star is, like in the previous example, I should have probably talked about example. M star is whether you donated or not, which is the same thing as whether you found somebody in the donation records. So suppose you want to know what's the
LinkedIn covariate that you wanted to add to your
Right. So in this type of surveys, if the validated donation, right, it's basically indicator variable for whether you were able to find the match in the donor records, and that's used as a covariate in the regression. But obviously, this has an error. Sometimes you falsely match, and other times you don't match. So even if the merge variable says 1, that person may not be a donor. And even if the merge variable says 0, that person may be a donor. And the way to account for that is to use the probability as a covariate instead of 0, 1. And in the likelihood methods, you can also weight the log likelihood. Similarly, if the donation is a dependent variable, then you can basically use you can regress the probability on the covariates of interest. And so this accounts for the uncertainty that's involved in the margin process, as opposed to treating the margins as true matches. Okay, so here's the example of that. So here on Huber in the original article, regressed ideology score. It's a little bit tautological because this ideology score is derived from the donation records. But setting that aside, so regressed the ideology score on the indicator variable for being a donor. So this is basically whether you are able to find the match in the and turn out and other demographic variables. So we're going to use our margin indicator and posterior matching probability to see how the results change. Okay. So in this case, it turns out the substantively results are similar. This is what they did using the proprietary method. Our coefficients are a little bit smaller than what they reported. Similar thing for Democrats. Our coefficient seems to be a little bit smaller than the proprietary method regression analysis. So the results are similar, but it seems there's a overestimate, compared to what we. So this is the posterior probability, and this is the dichotomous 0, 1 based on our algorithm.
Could you please remind what's Y again? What's
Why is this ideology score? So they're interested in whether donors are more ideologically extreme. The answer is yes. And and then how much so. So that's why they regress in the ideological score on the whether you donated or not. Okay. So the second application I want to talk about is the margin project that motivated this whole project. So we wanted to merge these two national voter files. So here I'm going to use the 2015 and 2016 voter files with 160 million voters each. So we have access to the entire country national voter file for each state. Okay. So almost all merging is done within each state. That makes sense because most people won't move, so it's much easier. And also the voter files are collected state by state. So there's all sorts of little differences that's really annoying. And so doing that merges within the state makes sense usually. But some people move across states, like I did, well, just once. But, and if you look at the IRS statistics of income migration data, so this is a really nice data set that's available online that tells you, based on tax filing, how many people move from one county to another. According to that, 9.2% of residents move to a new address in same state. So people move within the state. This is the same year, 2015, 2016. 1.6% moved to a new state. So there's a small number, but there's some people move. Okay, and about 90% of people didn't move during this time. Most common move is New York to Florida, looking for sunshine, and from California to Texas, looking for good steak, or cheaper housing, with the same amount of sunshine. Okay, so we're gonna do a 3-step process of cross-state merge. We're gonna block by gender, and then we do some k-means again to keep the number of observations manageable, like few hundred thousand records. So first, we're gonna do within state merge to find non-movers, people who don't move, and people who move within the state. And then we take those people out. So once we do the match, we take those people out, and then run cross-state merge to find cross-state movers. So we sort of do this in the brute force. So it's 50 states, right, plus DC. Choose 2, and then you have to compare both directions. See what I mean? So that's like about 1,200 comparisons, plus 51 merges. So we did this over, actually, like last weekend, like this past weekend. But that's not on the laptop. That requires some serious cluster computing facility. But that's good. It's like overnight, over weekend thing. Not too bad. So we use the linkage field: first name, middle name, last name, date of birth, house number, street name. But these things, if you're looking for the movers, obviously address changes, right? So you don't want to use some of these fields if you're looking for the movers. So the movers are harder to find, not just because there are fewer of them, but because the address is changed. So the address fields are not going to be informative. Okay, so here is the results. So you can see, so this is, I'm breaking down by within state and across state. So we were able to match, so this, remember, it's 2 time periods of the voter file. So we are able to match about 90% of voters. We found them in the same state in the following year in the voter file. Okay, and about 1 to 5%, we found them in the another state. Okay, so if you remember the figure I quoted from IRS, that was about a little bit more than 1% of people who move across state at the same time. Now the voter files are a little bit tricky because they don't get updated frequently, and people may not register quickly enough when they move, and so there's it's hard to compare those two things directly.
When in 2016 does the voter file come from?
Yeah, so again, that's also an issue because it depends on the state.
Yeah, I mean, most people are updating the registration in like the 2 or 3 months before the
Yeah,
election.
we got this data in November of 2016, but that doesn't mean they were updated at the same, November. Yeah, so it's earlier than that. So every year we get data in November. So we're comparing that, but each state has different scheduling, update schedule. So you can see that might be an issue. And FDR, so this is the false discovery rate. It's we kept it low, so it's about 1% at most. And if we take the strict standard, it's less. If you do the exact matching, you can see you can find 60% of people within state, but very few in the across state.
I'm
Yeah.
confused how you get such a low across state FDR. Is that because it seems like as soon as you look at people across state, if you find anyone in the United States that's registered with your same name and your same birthday, that's all you have to go on. It seems like you're almost guaranteed to find somebody somewhere that matches you if you have a common name. And so you're either going to say they're a match, which means that your FDR should be really high, or you're going to say they're not a match, and then you're not going to get any matches.
Right. So you mean the across state?
Further across state. Yeah.
Right. Yeah. So. Yeah, that's a good point. But remember that we subset it out. So if you did the within state march where we use more information and then find them, we take those people out. So once you do that, when you're doing a cross state march, you're basically getting 90% of the data already.
But when you do that with it, so I guess another question is if someone moves out of state, but they don't cancel their registration,
Right.
State,
Yeah.
then you're going to match them. You're going to match them locally, and you're never going to even check that they've merged.
Right. So
or that
they
they've moved. So the only people that you're
Right,
ever
that's
going to
true.
notice a move are where
right.
if the state cleaned up the voter file and said they're no longer on the
No,
file,
yeah,
which
yeah.
is I'm told unlikely, or they have a weird situation where you just couldn't match them anyway.
Right. So we're
Then you
missing.
even look.
Yeah. So in those cases, we're missing a lot of people who did who didn't file change of address form, and hence the state didn't do anything yet or hasn't done anything yet, and so it looks like it's a within state march, but they may have moved already. That's right.
It also means that all of your out-of-state movers are, in some sense, a peculiar subset of the people who moved. They're going to be unusual in some way because
Right, that's right. But that information is not, clearly not
Yeah.
captured in here, so there's no way. And so this is the I think argument that like these numbers has to be treated carefully because now like Republicans are pushing, like, oh, you find all these people, registered in multiple states, and that's illegal, and so there's a lot of politics going on. We should purge a lot of non-voters from the voter list because we don't want that to happen. But then, there's these lags on data collection and these issues come up. So yeah. So, I'll take this as
You can actually use your algorithm to clean the data first.
Right,
See
that's
if
true.
Find some of the matches.
Right, that's right. Before states clean it.
So, like
At some point, hopefully, there's a national registration, voter registration database, but that's not going to happen. That's not going to happen in the near future. Yes.
no, so what, the 0.62 is wrong, and we should contrast that with 5.12.
Right. Right. So this is the number of people we found in another state in the following year, and this is the percentage of people who we think are actually wrong matches among
But it's .62 divided by 5.1.
Oh, I see. Yeah. That's right.
So it's
That's
like
right. Yeah.
10% or
So
something
yeah,
like that.
that's right.
It's
So
not quite such a
yeah, you
small
can
number.
represent in two ways. Yeah, I made it so that this adds up to this number. But you're right. Yeah. So you could. It's a lot bigger. Yeah, that's right. So actually, that addresses. Does that make sense? Thanks, Chris.
10% still seems really.
Yeah, so among the yeah, so you're interpreting different. Yeah, so it's a 0.60. So you can think of it as this divided by that, which is much bigger than 0.62%. Yeah, I think we have another table that does that, but anyway, yeah, I forgot about that. Okay. And then this is the false negative rate. So there, the proportion of people who are missing. And again, this needs to be compared with this, right? So you're still missing a lot of people. Yeah.
So when you find someone who's in a cross-state match, like for the average person, how many people do you think they've matched with? So like how many people in the kind of period forward have a very high probability of being a match? Because if that's like high, then you might worry that you're just picking people that happen to be named the same with the same birthday. But if it's like one person, then I don't know. Do you have a sense of what that is?
Say that again.
So imagine you have like John Smith on some day.
Right.
If you find that he's a good match with 5 other John Smiths across 5 different states, he'll show up as a match, but you don't really know which of those 5
Right,
it
which
is.
of
It's
those.
not really a match
Right.
in the kind of way we'd think about it. So do you
Right.
know on average how many people anyone matches to in the next period?
Right. So the common name can be downweighted by the prior. So if there's a frequently occurring name, you can actually calculate the probability of random pair being having the same last name. So you can use that as a prior, and I'll talk a little bit about that. So that's how we deal with that issue, the common name issue.
But you could tabulate for every person that you think is a cross-state match. You can make a table counting the number of matches those people have and look at the distribution to see is everyone that's a cross-state match, do they match 3 or more people, or are most of them only matching one person?
Oh yeah, certainly.
And
Yeah,
that'd be
we
an
could.
interesting diagnostic.
Right. We could certainly do that. Right. Yeah. So the name differentiation, the only thing that distinguishes different posterior probability is that agreement pattern. So if it's not reflected there, it won't be reflected in the posterior probability unless you put the prior on the different names. But yeah, so you get this table. So we have nice summary function that provides these tables. So you can go and actually look at what are the matches that you're getting. Although in this type of data, there's so many people, right? It's just 160 million is a lot. So here's another plot. The top row is a within state match, and bottom row is a cross state match. And this is the distribution of the posterior probability. And you can see very clear separation. So these are ones, probability close to 1, and this is probability close to 0. So this is all pairs that we used to do that within state merge across states. So here's the match rate by states. So, on average it was 90%, but there is some variation. And this is the error rate. So the states like Wisconsin, Vermont, and New Hampshire, they seems to have much higher error rates. And I was quizzing Steve. Can you tell me why? And he has some ideas. But
have you thought about? I mean, I don't know whether this would show up in either the discovery or the negative rate, but whether these things correlate with mobility rates and that sort of thing. That maybe in places where because there is a lot of variation within and between states on mobility rate, and whether you might find more, I guess maybe false negatives in states that have high.
But you can see it's sort of correlated. Yeah, and also my hunch is that it's a voter file issue, because you also see these names for the across state match errors. So I have to look at it closely, but these states must have, maybe a lot of missing data. One thing I know is that the date of birth is missing for a lot of some of these states, not all.
Yeah. The other thing I was going to say is that there's considerable variation in how states manage, how top down or bottom up the states are in terms of managing their registration systems.
Right.
So a state like North
Yeah.
Carolina, if you move within the state, it's going to automatically cancel your. If you move between counties, it'll cancel your old record automatically.
Right.
Whereas like Vermont, which is really high up there, if you move between jurisdictions, then you might maintain a registration record in the other one.
Yeah, so that might
Exactly
make
what's
it
going
hard.
on.
Yeah, that's all American federalism. Basically. Okay, so that's basically the results. And then here, I don't know, this is, so we try to sort of plot the movers. So this is on the y-axis, it's the state of origin. And then on the x-axis, it's a destination. Might be probably hard to see. And this one is from our match rates. And on the right, you see the IRS data. And the correlation is about 0.3. We seems to recover the outflow of movers to California and Florida, but we seem to have a harder time finding movers to Texas than the IRS claims to be. But we see, like, if you look at California, there is like a cutters. A lot of people going to California, and that's the same in the IRS record. The same thing for Florida. If you see, like, there's the Florida line here, and the same thing you can see in the IRS record. So there's some correlation about 0.3, looking at the movers. And we can even do this at the county level, but we haven't made that plot yet. Okay, so the last thing I want to just mention before I wrap up is the use of auxiliary information as prior distribution. So I mentioned that the name can be differentiated by looking at the common frequency of the names. We can also, if you think IRS data, for example, movers data is a good one, we can actually incorporate that into our estimation. So for example, we can, if we know within the state, if we know the proportion of, so this is like, if you know non-movers and in-state movers, so they're people who are, the proportion of people who are matched within the state is a combination of the people who didn't move and people who moved within the state. So we can use that as a way to inform the parameter. So this is one of the parameters in the model. We can also see if it's in-state movers, the probability that the address doesn't match is a proportion of the in-state movers divided by in-state of movers and non-movers, because these are the people who are matched. So these are model parameters, so you can basically use this type of information to inform how big these numbers should be. We can do the same thing for the across state. So if we know outflow from county 1 to county 2, then we can divide by the total number of pairs to inform the proportion of the matches across state. So this way, like, this model is, and then computation doesn't increase. It's the same exact computation, and runtime doesn't increase. So it's a very simple way of incorporating extra information. Okay, so just to conclude and then discuss some of the things I'm doing right now. Margin dataset is a critical part of social science research. So used to be data merging is like you hire some RAs and can you merge these two data sets and come back with a single data set. Not so easy when there's no unique identifier, right? Who knows that RA, what that RA would do. And the large data sets make merging even more challenging. So even the deterministic merge, if you have millions of record, you still have to do comparison. So it's quite a challenge. EM part actually takes very little time. So it's really the counting, matching, and counting exercises that takes a long time. And yet margin can be consequential, right? Oftentimes we merge because there's some interesting information that are common, that you can bring on from another data set. So all this seems to suggest the margin should be part of replication. Okay. Like you should know how exactly people marched in order to actually understand the results that we see. So it's no longer just the final data set that's somehow magically merged out of several data sets. So we offer first principle scalable margin method that can incorporate auxiliary information. There's open source software we're going to release maybe in a few weeks. If you're interested, just email me. You can use the beta version. It seems to work really well. So our goal was to do this type of merge with a couple million records on the laptop, right? So that you don't have to have access to the cluster computing resources. We're doing more applications. So we're doing the merging CCUS with voter files. So that's a controversial territory, the voter validation. We also convinced NES to try our method instead of rely on just the catalyst validation. And another thing we are interested in is the stochastic blocking. So right now we still have to do some blocking to make the total number of records to 500,000, like 500,000. Like beyond that, it gets very difficult. But those are deterministic. So you can imagine doing that more stochastically blocking, clustering similar observations, and then doing merging within that. The real thing I really want to do that I have no idea how to do it yet is that merging with more than 2 files over time. So now I have opportunity. So the company called L2 I've been working with, they basically give me a data for each state whenever the voter file gets updated for each state. And the timing is different, and it comes every few months for each state. And the question is how you link all that over time. And each one has 160 million records. So it has to be something pretty simple, but then exploit some overtime structure. And if you can do that successfully, there's lots of interesting questions you can ask about like residential segregation, where people move, how that's related to the politics, and so on. There's also open problem that I haven't really thought about is the privacy preserving record linkage. So there's if you're a computer scientist, this is something really important. In fact, if two parties have two private files, and each one wants to get some information from one another, but you don't want to give out the whole data set, right? How would you do that? It's unclear. So we actually face this situation because CCS doesn't want to reveal their respondents' names and addresses. I don't really want to give out L2 data as well. So, but we want to merge. Well, at least I want to merge. Then how would you do that in a way that's secure and ideally you want to do it over the internet? And so there's a lot of interesting issues. Yeah, Chris.
So the Public Health Network in Massachusetts and the opiate stuff is doing exactly this. And the way they're doing it is files are only connected sort of in memory. So it's never the case that
Right.
these things get merged
Right.
onto a hard disk, whatever. And you might want to contact them.
Okay.
I can try to remember the guy's name. Sort of dig it up, but
Right.
as you might guess,
Right. Right.
an opiate crisis, the issues of privacy are like enormous.
Right. Right.
They managed to get this through the lawyers. And, I guess the only thing is it's all in SAS.
Okay. Yeah. That's right. That's right.
But they're public health people. What do you want?
Yeah. One interesting is that the EM, the output table that I showed you, has no privacy information in it. It's only the agreement patterns and the posterior probabilities. So if one party is trusted to run the merge, then you can do that without revealing any individual information. So that's one nice thing about this, and that's how we did the CCS and DIME merge, is because the CCS didn't want to reveal the individual names. We basically told them, just give us the EM table, and then we'll tell you where to do the cut. And so that's one way that this method protects the privacy. But you can use this type of method find out who these people are. So it's a dangerous tool to give out. So you have to be careful about the privacy issues. And yeah, that's all I have today. Yeah.
Was there any reason why you didn't use, say, information that's only available in certain states for some of these, so that you have race that's available in
Right,
a handful
right.
of states,
Right.
or party and partisan registration? Now, obviously, that's like checkered board across the country, but
Right.
it seems like the missingness would be okay.
Right, right.
But I wasn't sure if there was some reason why you just decided.
No, we just haven't gotten to it. But yeah, race would be interesting because there's also census data.
Yeah.
So we have we can have a good sense of with the name, sense ethnicity match, and we have a good sense of what the ethnicity is, even in the states where the race information is not available. So
Yeah, because I was wondering too about the
Yeah.
states that were doing poorly. I mean, some of them seem like very
Oh,
white
yeah.
states, and so there's less.
Right.
It's harder to the names might be harder.
right.
Whereas in states with multiple races or high diversity,
Yeah.
it's a lot easier to classify.
Yeah.
people based on the name.
Yes, Spanish names have accents and how they are
Yeah.
quoted can affect some of his. Ted, who is from Honduras, ensures that's okay.
Okay.
With our match, but I have no idea. But, yeah, so those I think auxiliary information. So what's nice about this model is that I think many of those can be incorporated. So basically, you have the probability of agreement given whether you're matched or not. And then you have the population proportion of the agreement.
And are when these kind of approximate times, are these like beta distributions or something like that? They're or priors. I'm just like.
Oh yeah, beta distribution. Yeah, we use the conjugate.
Yeah. So these are just where
Right.
you center the beta
Right.
distribution.
Yeah. But then you have to think about like how much you want prior to inform.
Yeah. Sure.
And yeah, you have to like put like very tight variance because it's a huge amount of data. So this,
Or otherwise it won't matter.
Right. Otherwise, like nothing changes. Yes.
Do you say more like descriptively like what the match rate looks like by age? Like older people easier to match?
Oh yeah,
harder to
yeah.
match?
Yeah. So we haven't like had time to explore that. Like literally that figure I showed you was like produced yesterday or something like that. But I wanted to show something that I'm currently working on. So, but I'm sure there's variation in terms of age.
Have you seen, so there are like encryption algorithms that are basically just one way, so encryption without decryption. It's like homomorphic encryption or something.
Right.
You can potentially use that for the privacy stuff. Like it'd
Right.
basically be there's some sort of shared
Shared.
encryption key
Yeah.
that creates like a similar like one-way mapping
Right.
that can't be reversed, and
Right.
then that information could then be used to merge because those values are like comparable.
And there has to be somewhere where the merge actually happens. Or
Yeah, exactly. Yeah, so it'd
Right.
be like it'd basically be like a one-way like transformation of the
Yeah.
data,
Yeah.
but a common transformation.
Right,
So that
right.
equal values of
Right.
each thing would end up in the same space.
Right.
Yeah.
Yeah.
I don't know those algorithms.
Yeah, I mean, I think it would be
This way,
fantastic
yeah.
if or maybe IQSS would do it, but like if there is a common platform where like two parties can say, hey,
Right.
can I match my data with yours? And then sure, and then like,
Yeah.
send the data there, and then the merge happens, and then you get another variable back,
Right.
right? Without sharing the information. Because that's basically the situation. It's like, CCS have obligation to protect the names and addresses of the survey respondents, so they cannot release that easily to me. And I have sort of obligation for L2, so I cannot release everything to them. And then but I want to do the match. How should I do it, right? So there's a lot of situations like that.
I mean, there are a lot of possibilities, but you've got to convince a bunch of lawyers.
Right.
To allow you to
Okay.
do it. And
Right.
It's a whole different kind of problem.
I see that part of that. So the technological problem, and then there's the legal problem there. Yeah. Yeah. But I think that's to me that seems to be the future. I've been trying to pitch this idea to some of the computer scientists, but more data sharing in a privacy preserving way. Yes.
Could you say more about the k-means you do when you're plotting?
Oh yeah. Yeah, so there it's k-means are based on the actual variable, not the pairs. So variables for each record. So if it's so we have to like make it numerical. You mean how to do that?
Yeah, like what did you do, for example, to turn those variables into something you could do k-means on?
Right. So we just used like let's see, in the for these cases, yeah. So we did like data registration. We created basically like treat this as a like numbers like sequence, just a like integer sequence, right? And then create like the k-means based on like just basically turn the dates into a like integer, and if the dates are close, they're close on the integer as well. Same thing for the name, so you can do the you can turn these names into even the 26 integers, and then like which letters are used, how many times, frequency
Okay.
of that. But our like clusters are pretty big, so it's like 350 to 500K, 500,000. So it's just attempt to get rid of some of the very unsimilar like names that they're completely different set of alphabets are used. So it's like we just use a Jaccard like frequency of how many times that each letter is used in each name, and then same thing for the street name.
And did you try that as compared to something like Lefferstein distance?
We tried but we haven't done a systematic investigation, and so we need to probably do those kind of things matter, right? And taking like if somebody's name is like junior, like has a junior, or those things has to be taken out, and there's a lot of sort of pre-processing that goes on. Like some of the addresses are like PO box, and we get rid of those as well. Like the contribution data is like a lot of PO boxes, so we treat that as missing address. Yeah. Yeah. So I think these are like data specific issues that you have to deal with. If you're doing something medical records, you probably have different issues and stuff.
For regression, do you need to worry about how to compute the standard errors?
Right. So in our application, like there's no like standard errors are minuscule because the data is so big. The parameters are very, very precisely estimated.
So the fact that your matching probability was estimated.
Yeah, that doesn't really matter. Yeah. But in a smaller data set, that could matter. So you want to account for that as well.
Okay, thank you so much.
Yeah, thanks.